Right. Good evening, everyone. Thank you, ROOTCON, for having me here in front of such a lovely audience. I'm going to be talking about ExplIoT framework. Uh, so the talk is ExplIoT Hacking IoT like a boss. A little bit about me. I'm the co-founder and director of research at Party Software Labs. My core area is to focus on IoT security research. Other than that, I'm co-founder of a non-profit organization, as already mentioned, NUL. This is one of the most active security communities in Asia. This is this is a self-organizing community in the sense that we don't have any findings from any major corporations. All the volunteers come together in different chapters, different cities, and conduct monthly meetings for free for anyone to attend. So we have around 9 chapters in India. We have one in Singapore, one in Dubai, and one in Amsterdam. And if you guys are interested to start one here, just shoot me an email. Besides that, we also run 2 security conferences called ROOTCON, which is organized in Goa, India, and hardware.io, which focuses on hardware security, and this is organized in the Netherlands. I do trainings. I do a training called Practical IoT Hacking at most of the security conferences like Black Hat, Factory Palace, ROOTCON, and a bunch of more conferences. And I just write some software whenever I have free time. Alright, so enough of self-promotion, let's get into the meat. So I'm going to be talking about what are the IoT security issues, what is the attack surface according to me, and what is the problem that we have with the IoT. And then I'm going to talk about the framework that we are coming up with, or rather we have already released it, and give you small demos of the framework and what things you can do with the framework if you want to security test any IoT ecosystem. So as far as security issues are concerned, IoT is at the same place where software security was in the 90s. I mean, there is no or low motivation for security, maybe for budget reasons, or people are simply not aware. So let's face it, most of the startups that you see, IoT startups, they're not hardware manufacturers. They are IoT vendors. So they take the hardware from the manufacturers and trust that the hardware will be secure and build their applications on top of it. The other issue is power and cost limitations of small sensors. So when you have really small chips which do not have enough power or capability to do a certain level of encryption, then you're left with nothing else but either ship the same device or buy an expensive chip. The moment you decide to buy an expensive chip and put it in your sensor, your competitors are going to beat you. And then the next is protocol, which is very interesting because in the products that we have seen, we have researched, we see that some of the startups, what they do is they simply don't use any known protocols. They say their ideology is that the communication is very simple between the sensor and the gateway or the cloud or the mobile. So let's just have a simple format for communication exchange, and we will build security on top of it. That's a very bad idea. The other problem with IoT protocols is that most of the IoT protocols are built for automation. So there is a provision for discovery in most of the protocols. The whole idea with IoT or smart devices is that they are supposed to make us lazy. No, we are not supposed to work. So they should be auto provisioned. So you just buy the stuff and you place it, and it will auto provision itself within the network. And that is good for security folks or people who want to break the security of the networks, because these discovery mechanisms give you a lot of information about the network and the device which you can use to again launch your attacks. I'll come to the latest, the cloud part later, the trust and telemetry data, and we'll see a simple example, but this is a generic problem. and we're going to see a lot of problems where sensors are going to attack the cloud. All right, so the attack surface at a very high level, if you look at the components of an IoT ecosystem, you have the device itself. And when you look at the device, the common attack surface on the device is the software that is running on the device. For example, if it is running any kind of service, a code server, an HTTP server, if it has Linux-like OS, maybe SSH, HTTP, FTP, whatnot. External storage, USB, SD card, the firmware update as well as the firmware encryption mechanism. The underlying hardware itself, the debug ports on the hardware, the memory chips on the hardware, the sensors on the hardware itself. And then finally, if the device does radio communication, then the radio protocol flaws as well as the implementation flaws of the manufacturers. Next is the cloud, and cloud is pretty much standardized if you compare it from the sensor perspective or the hardware perspective. You have standard issues like communication, storage on the cloud, business logic flaws in the implementation, and robust web top 10 or standard web security issues or API security issues. And the final one is the mobile. This becomes integral part of IoT because this is where the users get the value in the device. And this is again more or less standardized as compared to again hardware. You have standard issues, communication, storage, mobile top 10 from OWASP or any standard mobile security issues. So based on this, OWASP has come out with an IoT top 10. We looked at the OWASP top 10, but I mean they've done a good job, but we were really not convinced because the results of our penetration tests for customers as well as research showed that there were different type of vulnerabilities that were there. And OWASP was more focused on standard vulnerabilities and pretty much less focused on the hardware itself. So I'm not going to cover the top 10 vulnerabilities. If you're interested, we can have a discussion after that. But this is more focused on the perspective that we looked at our reports and we saw which vulnerabilities. So we calculated all the vulnerabilities that we had found, and based on that, then we came up with our own list of which is the most crucial set of vulnerabilities in IoT. All right, so this is us in 2013 when we started to go for professional pen testing for IoT products. So you get a customer, they say, okay, I have this interesting product, this sensor, and you have to pen test it, and you're really happy. So we're going to break this stuff, looks pretty interesting. Just take care. So yes, we are really excited, and what you would think is that we are security experts and we will beat the shit out of this product. All there is to this product is mobile application, cloud, blah blah blah, and the device. Yes, but what actually happens is when we get the device, and then we figure out there are just too many interfaces to test, not just the cloud. If you just look in the hardware, there are just too many things to test. And how do we test it? Then we start preparing all the hardware tools that are required, and every tool has its own interface, and then we go about studying the interface. We download open source software, protocol client software, we compile them, some of them don't work, some of them are not mature enough, and then finally we ended up building. I'm sure this is the story of most of the researchers who do IoT penetration tests. And then we finally ended up writing our own scripts for each and every test. And as we progressed, every product that we tested, we had to procure a different set of hardware and different set of tools or software. And that's when a couple of years down the line, we decided that's it, we need to do something about it. And we can't go ahead and keep on wasting a lot of time in first procuring and then learning the tool, compiling, writing our own scripts. It's just a waste of time. And that thought process continued for another a couple of years. And then we came up with this framework called ExplIoT. So this is a framework for penetration testing or security testing, whatever you want to call it, for IoT as well as smart infrastructure. And when we decided we were going to write this framework, the motivation was that it should be simple to use. The researchers should not waste a lot of time in learning. Most of the things which can be automated, we will automate for them, so that all they need is just one software to plug into any kind of hardware so that they can do any range of tests depending on what the IoT product or the target is. It should be extendable, as well as when somebody extends it, it should be fairly simple to write test cases on it. So considering, let's say you have uh, uh, an IoT product manufacturer, Sony, Samsung, whatever, and they have a standard SDLC process. This should align into their security test or regression test, and they should be able to write their own plugins and just run this automated tests before releasing the product. All right. So right now it is pretty simple. You cannot hack IoT like a boss, but you can pretty much do a lot of interesting stuff with the tool as of now. So the framework is simple. We have a protocol engine which allows you to communicate with the different IoT protocols, which includes your TCP/IP based protocols like COAP, MQTT, HTTP, radio protocols like BLE, hardware protocols like I2C, SPI, and then we have a base class. So all you need is just create your own plugin, extend it with the base test class, and there is a test suite class which takes all the plugins and feeds it to the command line interface, and all the user sees is the command line interface called EF console, and all you need to do is just run your test case and make sure you have the if you're doing a hardware or a radio test, make sure you have the hardware module with you. Yeah. So as I mentioned, all you need to do is just define the members of the class and override the three methods: pre, execute, and post. Only execute method is mandatory, and all you can do is just import the protocol, the required protocol from the protocol engine present in the framework. So this is just a sample plugin. This is there checked into the code itself. So let's go over the code. The first part that you see is the constructor or the init function. Within the init function, first you define what the test is, which is pretty simple, English. The next part of the init is defining the parameters for the test case, which are again pretty simple. They're based on R parser from Python. And then all you need to do is just define your pre-post methods if you need to do any dependency or setup or cleanup. If not, you don't have to define these functions. And then finally is the execute function, where you will put the actual logic of your test and use the protocol provided by the framework itself. And then depending on how your test performs, you can specify whether the test failed or the test succeeded. So the current plugins that we have within the framework, we have BLE plugins that allow you to do scanning, first test, read and write values to the BLE sensors. You have MQTT, which allow you to do authentication tracking, which allow you to publish and subscribe to an MQTT. I'll cover that in a little detail once after this slide. Modbus, you can read and write register and coil values to a Modbus slave. You can read and write onto the canvas. Serial is nothing but you can brute force serial communication or first test serial communication with the device, which I'll talk in detail later. And if the device has an SPI flash chip, you can take the chip out and extract the contents of the chip for checking for firmware, doing whatever, modify the contents and write back to the flash chip if you want. You can do the same thing with the I2C EEPROM chips as well. And I have two exploits as of now. One is for a BLE based lock, and one is for a smart lock. Alright, so let's start with MQTT. MQTT is short for Message Queuing Telemetry Transport Protocol. This is a standard protocol. The way it works is that you have a broker in the middle, and all the nodes connect to the broker. The nodes can be anything. It can be the sensors, or it can be the mobile device, or it can be the cloud, depending on where you place the broker. And you publish, so the way you would send data is that you publish message on a specific topic, and if you want to read that specific data, you need to subscribe to that specific topic. Now, based on the protocol standard itself, it goes ahead and mentions that, okay, you're free to use topics of the form some A/B/C/D, however you want, but you cannot use topics that start with a $sign, or more specifically, topics that start with $sys, because they are supposed to be used by the backend, not by the application code for maintenance or whatever purpose. And that is the first thing that, as a security researcher, you will do is, the moment you find an MQTT broker running, the first thing you will do is check for $sys topics, because they'll give you a lot of information about the broker version, software, clients that are connected, which topics are the clients connected to, and so on and so forth. The next is denial of service. So we looked at few implementations, popular implementations of MQTT. We've not reported it to anyone because I'm not sure whether they will consider this as a vulnerability or not. What happens is, in MQTT protocol, you have authentication inbuilt, which means you can specify username and password. But on top of that, every node has to specify a client ID. And typically, sometimes what the vendors would do is they would use client ID as authentication itself and just do away with the username and password. Now, this client ID is pretty interesting because it's not a secret. The client IDs would typically be hard-coded or would have a standard generation mechanism within the firmware or the mobile device, mobile app, and it's easy to find out. So the moment a client connects to the broker will check whether there is in the list of already connected clients, is there any client with the same client ID? If there is already a client connected with the same client ID, it will disconnect the old client and let the new client connected. Which means that if you get into the network, you know how the client IDs are going to be generated. You can just start connecting to the broker and start disconnecting all the connected clients that are there. The most famous implementation is Mosquito for MQTT, which has this behavior. AWS also has this behavior. The only thing is AWS mandates authentication. I have not tested this, but I think authentication has nothing to do with the client ID checking logic. And the last one, authentication brute force, and then the malicious telemetry data. This is very, very interesting. I think part of this was also covered in the previous presentation as well. What if you feed malicious input? to the system. So, and this is not specific to MQTT, this is a generic problem. I foresee that this is going to happen a lot because this is going to give you access to the IoT ecosystem. So what you can do is, if you can act as one of the nodes within your smart infrastructure and start sending data back to the cloud, instead of sending write data, you can start sending malicious data. We look at the demos for this. So let's start with the MQTT auth. Alright, so I have a local Mosquito server running on my local machine, which has two usernames, user and user1, and the password configured. Just fast forward it. Okay, so I run the server here, and then I connect to the server using the framework itself. So there are two commands, list and run. List will give you the list of plugins that are installed, and run will allow you to run a particular plugin. And if you want to see details about plugin, just use --help or -h, which will give you the details about the plugin. And then you can go ahead and run the plugin as you feel like. So here I'm using the correct username but a wrong password, and just to show if you want to specifically check on one specific username. If you want to just force download any password dictionary that you have and pass the dictionary to it and start brute forcing the server. So it's pretty simple. Verbose mode, and you can see what happened with each and every user. Alright, malicious telemetry data, as I said, having your root device within the network and sending data back to the cloud. What you can do is two things. One of the things was again already mentioned on the previous presentation as well. You can send bad data, which will corrupt the system or the cloud storage, and then you would get wrong values. The other and more interesting thing is, instead of sending valid data that the cloud expects, you still have access to the cloud, and if you can figure out where your data is being stored or where your data is going, you can also apply standard cloud attacks or standard web attacks. So here what I'm going to do is, here the example is that this is a temperature sensor in an engine room or boiler room, and an administrator has access to a web interface to monitor the status of the engine room. And for example, I've taken the MQTT protocol sensor. So the temperature data from the sensor is going to the cloud using MQTT. So here I'm just running again my local server. Now, because of the testing, let's say I know that my data is being presented to the admin on the admin web interface. So the easiest thing to do would to check if I can somehow attack the web interface of the admin console. You can do whatever depending on how the cloud or how the web interface is, or what the cloud implementation is actually doing with the data that is being sent by the telemetry device. So here I run a publish on a topic called temp, which I have created. Anyways, this is the standard way in which any developers would create topics, and you can find that out from the firmware or the mobile application. And here I start the application, assuming now the application is fetching data, temperature data from the sensor through the cloud interface. So I send the temperature information. it gets the temperature information. Then I send again temperature information, gets the temperature, right temperature information. Now I know that okay, the temperature is being printed here. So let me just send an XSF payload and check. Here you go, and so now I have a vulnerability because I know that the web interface is not filtering the telemetry data that is coming in from the sensor. All right, BLE. BLE is now widely used in many products, especially lifestyle and health monitoring products. Uh, and one of the common issues with the implementations is that most vendors now do not do any kind of pairing, which means the moment your device or your sensor is free, anybody can connect to the sensor and read values from it. So the way you would read or write data is BLE Bluetooth protocol. The BLE protocol has something called as GATT or the attribute protocol, which specifies characteristics, and those characteristics will store the actual data that you will send, you will write to and read from. For example, if you want to configure time on your watch, you would write to a specific characteristic and write a specific value, which will change the time to whatever time you specify. Now, this is an interesting aspect because then it gives you access to reading and writing any kind of values on the PLE devices. Plus, with the framework, what you can do is not only read write, but you can first test the characteristic value as well. So let's quickly do a PLE plugins demo here. So there are three plugins: BLE Scan, BLE Cab Write, four: BLE Cab Read, and BLE Cab Fuzz. You can, as soon as you get a device, you can scan for the device in the vicinity. If you want more information, you can use the Windows mode to get more information about the device. Once you find your target device, take the MAC address and then scan for services and characteristics on the device itself. So here I'm searching for characteristics, and it gives me a list of characteristics. Characteristics are identified by a unique UUID or can also be used for communication using a handle value. Now I'm in this example, I have a BLE watch that I'm trying to communicate with, and obviously I'm going to set a specific time on the watch. Now, if this works, this is an issue because then you can write to any specific characteristic which the device allows you to write. So go ahead and write. So I don't have the watch, but this basically changes the timing. Now I take this, and what I can do now is I can start fuzzing this specific characteristic or all the characteristics that I can write to and see the behavior of the device. So in our tests, we were able to crash the devices, and we were, in some cases, we were able to change it to DFU or firmware upgrade mode. So we'll just start sending random values. The moment this thing fails, that's the time when you know that the device has crashed and is not responding to your requests anymore. Oops. Right. This takes us to our next exploit, BLE based exploit. So there is this company called Taplock, which came out with this advertisement called Unbreakable Design. This is a BLE and a fingerprint based lock. So you can store a fingerprint and then you can open the lock with a fingerprint. Or if you don't want to touch this, you can open it through your mobile app. There's a researcher who goes by the handle Cybercriminals. His name is Andrew. He's from the UK. He bought this device and he quickly figured out that the way the mobile app is communicating with the lock is using statically generated information and not any kind of authentication. So I requested him for the details and I just quickly wrote the plugins based on his research. Now, the interesting fact here is that this particular plugin, Tap Unlock, I call it Tap Unlock, this will scan for all the tap locks in the vicinity and then you can open each one of them individually. And I think by now they have fixed this vulnerability. I don't know how many tap locks are already available in the market or already on people's doors. All you need to do is just run this. Get the MAC address, create the static information, send it, and open it up. Alright, UART, one of the very interesting aspects of hardware devices. UART is Universal Asynchronous Receiver Transmitter, basically used for serial communication. So two components on a board can talk to each other using two-wire bus, TX and RX. And it's serial communication, very simple. The other usage of this is that hardware manufacturers, what they do is they will put UART lines on the board itself, enable them, so that if you connect to those UART lines, you can basically get the serial connection to the firmware. Firmware, OS, whatever is running on the system. Now, this is again a standard practice to have a UART port on the board, and for Linux-like OS on the devices, you would typically get a shell, most likely a root shell, or you may get a custom shell, which may have its own issues if not properly tested. And then you may also have hidden commands which give you more privilege on the device itself. So for this test, I have created this board called Diva IoT board, that means secure and vulnerable app for IoT. And basically this demonstrates all the security issues that a hardware can have. And I use this for my training. But regardless, there is a hidden command on this, and the way you would go about brute forcing serial communication is pretty simple. And this is not just useful for finding hidden commands, you can first test the command shell itself. You can first test any parameters on the command shell. So first I will log into, I'll connect the device, use the serial connection, connect to the device and get the UART shell or custom console over the UART. So once you run this, the device gets connected to the DY0. Once you run it, you get a custom console which is written by us. And if you write any invalid command, it says invalid input. Pretty standard. Once you write a valid command, it will give you standard input. So now I know that for any invalid command or wrong command, I get a response for an invalid input. Now I take that as a match criteria for invalid or wrong commands, and I use the serial brute force or serial brute plugin and specify that criteria and say generate 4-character strings and start brute forcing the serial communication on the device, and stop when you don't get the string invalid in the response. Pretty simple. So you can specify the length, any prefix that you want to send across, you want to append anything to the string, and you want to give any match criteria or you want to give any no match criteria. So in my case, it's no match criteria, which means if it doesn't have the string invalid, it's most likely a valid command. So then you go ahead and just run it, and it will generate the characters or all the permutations of characters. So you just start sending and get the response. The moment there is a response triggered, I know that this could be a valid command. So I go ahead and I can now verify on the device whether this was actually a command or not. So this becomes very handy because when you get a custom console, this will help you find privileged commands which the vendors will not publish either on any documentation or even in the help itself. I think I'm out of time, so just quickly. So you can do the same thing with, if you have a flash chip, take out the flash chip, hook it into an SPI connector and run SPI flash read to read, dump the data, change the contents, write back whatever you want to do. For Modbus, we just have the read and write coils and registers so you can communicate with the Modbus slave as well. For the roadmap, it's a quite big effort, specifically more on the hardware part and the radio part, because my plan is to include radio support as a whole for IoT, regardless of, or basically including all the protocols that are available, or all the famous protocols that are available. So protocols that are based on 15.4 standard, like Zigbee, Thread, 6LoWPAN, Wireless HART, other protocols like LoRaWAN, Z-Wave, and generic SDR capabilities so that if there is custom radio communication, you can still be able to scan through the vicinity, pick the communication, and then analyze the communication, reverse engineering the communication to see what kind of data is being passed between the nodes. More IoT protocol support, specifically for medical and industrial and transportation protocols, firmware analysis support, and more IoT exploits. I think that's about it. If you are interested in this, you can download the source code from GitLab, and if you want to contribute, just send me an email. I'm currently working on a contributor license agreement because obviously I don't want to be sued by a contributor if I make changes to his part of the code. Yeah. Any questions? Either everyone wants to use it or nobody wants to use it.
Alright, no questions? Going once, twice, thrice? Alright, I'll take that. Good things can find him, right? He'll be around until tomorrow.